Hello, welcome to part 3 of learning to program math functions with a computer. This is part 3b, where we're going to look more deeply into logarithms. We had used a binary base approach and using square roots to find the values of the exponents and logarithms of numbers. Now we are going to repeat the process using power series. The reason for this approach is to show how advanced topics such as calculus can be simplified and speed up the process for getting the answer. Even more interesting is that it allows us to better understand the theory of exponents and logarithms and their application. Let us look quickly at the theory of exponents and logarithms. First, we note that the power series for e to the x is 1 plus x divided by 1 factorial plus x squared divided by 2 factorial, and completing that process. This series is derived by using differential calculus. The log is defined as raising a number and taking log of the number of interest. We now show that using that formula and taking the logs of both sides, that we get the log of b to the base a times log of b to the base a is equal to 1. This is an important function when we want to convert from one base to another base. So for example, we're going to use the base e to find out our logarithms and exponents, but then we have to convert back to base 10 in order to find the logarithm exponent in our base 10 system. Another useful function will be b to the x. We now substitute b by its logarithmic form, and we get that that's equal to a times log a of b. Again, this will be useful in our power series when we want to convert from base e to base 10. The power series for the log can be derived through interval calculus, and finding the power series of that, we find that it's a little bit more complex. That what we have to do is find the value of x that will give us the number of interest. So we show in the 1 plus x over 1 minus x, we want to find, say, the logarithm of 2 or a. We then find out what x would have to be in order for that to occur. That's x equal a minus 1 divided by a plus 1. And we give an example here that to find the logarithm of 2, we'd have to substitute 1/3 for x. And now we also show, again, the conversion between bases and the powers. Now, to find the exponential function, this basically two parts are setting up for actually finding the answer. So, for example, over here we find the value of e using a function which we call ex, an extra x to distinguish it from other functions. And then we use the theory that we had for converting between bases. We find that base in the power. Okay, and then we get our answer. That's simple. Okay, now the function e, which we had called in order to get our answer, is what we eventually do here is, again, we want to find out what e is, and we then go through and correct for our exponent. So if it's a negative exponent, we're going to make a positive exponent, and note that we will invert our answer. We also want to get rid of the integral part, because when we use the power series, we don't want to have to use a lot of terms to get the correct answer. And so now we just have to understand what this function is in order to be able to do an exponential function. And this basically is the function for evaluating the power series for e to the x. One of the tricks we've used is we recognize that if we can make xi smaller, we can make the power series converge faster, and we won't need as many terms. So what we've done is we've divided it by 4, realizing that this gives us a 1/4 root. So then we will have to square our answer and then square it again to get the correct answer. This is a little trick to speed up the process. And now we basically implement the first 11 terms of our power series. One of the tricks we're using is we don't want to get big numbers divided by big numbers. So what we do is each time through, we multiply our x times the previous function times the next term in the factorial series, divided by the term in the factorial series. And then we add these terms together. So that's basically the work that we have to do in order to find a number raised to a power. Now we just sort of reverse that process for finding the logarithm of the number. Again, repeating the process of getting a bigger number so that we can get the integer part of that number out and just get the fractional part. So again, we have our setup function, which basically is going to be calling the log of e, which will show us a power series. And what we do again here is we get rid of the integer portion of our number that we're taking the logarithm of. Okay, and then we also, here we've done it with the base, we now do it with the number itself. And you'll see that this logic and this logic are identical. And we've now shown how to take into account that base. But we also notice that we have to now divide by the logarithm to get it from the base e to the base of concern. And now we have our power series. Okay, we've already discussed where this series came from. This particular term in here is to try to make the number that we're entering into that power series smaller. So we do that by taking the square root 3 times. And then by doing that, we can then correct later on for it. Okay, so now we go through, find out what EVX corresponds to x to make that, so x will give us EVX back again. And then we go through and we do the power series. This time we don't have factorials in there. So you'll notice that we're not dividing x, we're just dividing the x factor each time. Okay, and we're going in steps of 2 through the series. We're not going through, we're skipping out the even numbers in the series. And then when we're finished evaluating this part of the series, we then multiply by the 2 in order to get the answer that we want. And then we have to take into account those square roots of the mantissa that we had taken to return it back to its normal value. So this basically has allowed us to find the logarithm and exponential functions using a different approach. The advantage of this approach over part shown in part 3a is that it will operate faster because of the fact that we don't have to go through 54 cycles as we did in the previous problem. I have not compared the accuracy between the two series, but there are a number of techniques that we can show later on that would allow us to do this much faster. Thank you again for your interest.